And welcome to the combustion webinar. And today the 89th combustion webinar. And today it's our great pleasure to invite Professor Wang to talk about Soot diagnostics for laminar counterflow flames. And Dr. Wang is a professor at Wuhan University of Technology, and he also the director of Combustion and Laser Sensing Laboratory at WUT. At the same time, he also served as the deputy director of the Industrial Carbon-Free Combustion Research Center at the Foshan Xianhu Laboratory. So he received his bachelor degree from WUT and a master degree from Tsinghua University. And he obtained his PhD from the Clean Combustion Research Center at KAUST in 2013. So Dr. Wang's research interests include laminar counterflow flames, soot and NOx formation, ammonia energy, as well as optical diagnostics method in combustion environment. And Dr. Wang has published more than 100 journal papers, including a review paper in PACS. So that's pretty much the talk will be based on, I think. And also, most recently, his work has focused on utilization of hydrogen and ammonia fuels, decarbonize high-temperature industrial processes, such as the manufacturing of ceramic tiles. It's a very unique application. And also a development and application of laser-based spectroscopy methods for scalar measurement in harsh environment. So with that, the podium is yours, Dr. Wang, please.
Okay. Thank you, Professor Fang, for your kind introduction. It's a great honor today for me to have this opportunity to present to our international audience. So I would like to thank again the organizer for inviting me and for the organization work. So the topic of my talk today is about the diagnostics of sooting laminar counterflow flames. I will first give a brief introduction to soot and to counterflow diffusion flames and explain a little bit on why we favor this kind of flame for soot studies. So next I will discuss some diagnostics methods to measure the various scalar and the velocity field in sooting flames. This will include the soot volume fraction, temperature, species, and the flow field. And then I will talk about some modeling aspects, but not so much from the soot chemistry point of view, but on the specification.
Can you make the screen like a full screen of your?
It's not full screen, so I from my side it seems to me a full screen.
Maybe you share the other screen, the full screen, because what we see is only the slide, not.
How about now?
No. Okay, yeah, no, it's good.
It's okay. Okay.
Yes.
Sorry about that. Okay.
Yeah.
So I will next talk about some modeling aspect. Can you see the pointer? No. Can you see the pointer here?
Yes, we can see it. Good.
Okay. Thank you. So I will next talk about some modeling aspect, but not so much from soot chemistry point of view, but on the specification of boundary conditions, which I believe is very important to ensure meaningful comparison between numerical and experimental data. So finally, I will give a summary and discuss some future prospects. So first of all, some background on soot. Soot generally refers to the carbonaceous particles originating from pyrolysis or incomplete combustion of hydrocarbon fuels. And there is a lot of good reasons to study soot. First of all, soot is a visible emission, so it's unpleasant to see and can cause public awareness. And second, soot is arguably the second largest contributor to global warming. So cutting soot emissions in line with the global target of reducing greenhouse gas emissions. And soot is also known to have negative health effects, and soot deposits in practical combustion devices can also affect the system durability and also sometimes the efficiency of the devices. Last point, which is quite interesting, is soot sometimes is very necessary to ensure proper operation of practical combustion devices. Notable example is this coal-fired industrial boiler, where soot is very important for enhancing reactive heat transfer between the flame and the working fluid, which is most cases water. But nonetheless, there is a good incentive to mix coal with ammonia as a means to reduce CO2 emissions. Hehowever, if you mix too much of ammonia, the soot formation will be significantly reduced. Coming with it, the reduction of flame heat transfer, reactive heat transfer. This can actually cause a lot of problems in industrial boilers. So we actually meet these problems, and there are some. We need to find some solutions to enhance the heat transfer or to change the boiler structures. So actually, this is a very interesting point. But all of this just says that there is a need to actively control soot formation. So a prerequisite to do that is that we have to understand soot formation very well. But unfortunately, soot formation has proven to be extremely complex. So it includes complex interactions of a lot of sub-processes. For example, you have fuel pyrolysis, you have precursor formation, you have soot inception, growth, oxidation, agglomeration, and a lot of that. And to make things worse, each of these sub-processes is also complex by itself. So here I give two examples, which one of them is pH chemistry, and the other one is soot nucleations. There is a lot of unknown details about these processes. So this actually makes Miller and co-authors in 2005 wrote in their review papers that hopefully whoever writes this review in 2054 will report that there is then a complete quantitative understanding of the mechanism of soot formation in combustion. So this simply means that everybody agrees that soot formation is very complex, and of course, fundamental studies are required. Soot formation, because they are very complex, they are actually affected by a lot of parameters. And for fundamental studies, so you will certainly do not prefer practical flames where you have so many influencing factors that it is difficult to decouple. So actually, soot researchers prefer laminar flames with highly controlled boundary conditions. So if you go to the literature, you will find three types of flames that is mostly favored by soot researchers. The first one is very simple flat premix flames. Second one is cold-flow jet diffusion flames. And the third one is the counterflow diffusion flames, which is the primary focus of today's talk. Here it just shows flat premix flames stabilized on a commercial mechanical burner. So when you run the fuel reach, you can have a sooting premix flames. The flow field and the flame structure are very simple and easy to analyze. However, the major drawback of this type of flame has to do with the fact that many practical soot emitting devices actually rely on turbulent. Sorry about that. Any problem with the collection?
Yeah.
Is it resumed?
Yeah, you share your screen again.
I have to share the screen. Okay. So what's the problem?
Yeah, I don't know what happened.
Okay. So I will resume.
Yeah.
Is it okay now?
Yeah, full screen. Yeah, you go to
full screen. Is it okay now?
Yes. Now it's
okay. Sorry about that. Okay. So let me bring the pointer on. So the problem with premix flame is that in practical combustion devices, for example, diesel engines and jet engines, they actually rely on turbulent diffusion flame for operation. So in this sense, this may be more relevant to study diffusion flames for soot formation. So I think the largest portion of soot studies are done using cold-flow diffusion flames, which is very easy to establish. And this type of flame can also be easily installed in pressure chambers, so you can study the effects of soot formation. But one thing that is probably not so nice is that this type of flame is actually two-dimensional, and the flow field can be more complex than you prefer. Although the flame looks quite simple, so under the hood, the flow structure can be quite complex, and this is probably not the best option if you want to study the fundamentals of kinetics. So counterflow, in my opinion, is the simplest diffusion flame that you can establish in a laboratory. So you simply have a fuel and an oxidizer nozzle opposing each other, and you have a flat flame established in between. The benefits of using counterflow flame for soot studies is, first of all, it's a quasi-1D dimensional, so it's favorable for measurement and modeling with complex chemistry. And also, it's a highly controllable boundary conditions. And you can easily change the strain rates, which is quite difficult to do in cold-flow diffusion flame. The counterflow flame has a very close relationship with the Laminar Fleming model, which is widely used for the modeling of turbulent diffusion flames. So in that case, information about soot formation in counterflow flames is beneficial to the understanding and modeling of practical turbulent sooting flames. Okay, next I will briefly introduce the general sooting structures of counterflow flames. Sooting counterflow can be generally classified into two distinct types, depending on the relative position of the flame and the stagnation plane, which is a plane where you have zero axial velocity. In the first time, what we call these soot formation flames or SF flames, the flame front is on the oxidizer side of the stagnation plane. So in this type of plane, once soot formed will be convected away from the oxidizing flame front, but toward the stagnation plane. And during this process, soot will continue to grow in mass and size, but does not experience much oxidation. So under the stagnation plane, it's difficult for the soot particles to penetrate to the other side because you can only have diffusivities, but the diffusivity for soot particles is very small as compared to these gaseous counterparts. So this will actually result in a very interesting profile for soot volume fraction if you plot it across the center line. So you have soot growth, and then you have a sudden drop of soot volume fraction across the stagnation plane. So what physically happens is these accumulated soot particles will emit through radially in a stagnant plane and get mixed with in the environment. Another type of flame is what we call soot formation oxidation flames or SFO flame. So in this type of flames, flame front is on the fuel side of the stagnation plane. So when soot formed will be convected towards flame where it can get oxidized. So if you look at the profile, you will see the first increase representing soot formation and the decrease representing soot oxidation. So this type of flame can be made completely soot-free if all the soot particles formed can be oxidized. This is in contrast to this soot formation flame where you have the smoke leakage from the flame to the environment. So these are the general structures of these two different types of counterflow flames. Okay, so now we can move to discuss the various diagnostic methods for sooting counterflow flames. First, it's very useful to emphasize again that this high-quality experimental data are essential for understanding and predictive modeling of soot formation. And when we say high-quality data, we actually mean a lot of things. So data should be comprehensive, since many factors would affect soot formation. So first of course, we need to have data on soot. That means you need to data for soot concentration, and ideally you should also have information about size distribution, morphology, and soot chemical composition. And also we need accurate temperature data because temperature is a very important parameter that control all reaction rates. And the species mole fractions are important because along with temperature, they actually provide a thermochemical environment for soot formation. Finally, the flow fields give the residence time and the trajectory for soot, and it's also needed to be measured accurately. Another point is about this experimental determination of boundary conditions. I will come back to this point later, but here I just want to mention some measurement challenges that are specific to counterflow flames. I think the challenge mostly comes from the fact that the sooting dome in counterflow is very narrow in distance. So here is a mid-secondary signal from soot particles in counterflow flames. We can see the thickness of the sooting region is only about 0.5 millimeter, so about 500 microns. And you have to, in this 500 microns, you have to need high resolution, high spatial resolution to resolve this soot volume fraction in space. because without that you cannot get the many interesting parameters you want to measure. For example, soot production rate is actually the derivative of this profile, and this is a 500 micron region, so you can imagine that there is quite some challenges for measuring this accurately. So in this talk, I will first discuss this soot volume fraction measurement. One of the typical methods is spectral soot emission. The spectrally resolved spontaneous emission of flame-heated soot particles actually provide information on both soot temperature and volume fragrance. Here is a typical setup, which is very simple. You just need a positive lens to collect the radiation from soot and then send it to the spectrograph to obtain the spectral information. So here I give you the equation linking the measured quantity, which is the local soot spectral radiation intensity, and the desired quantity, which is the soot volume fraction. You can see there is a very simple linear relationship. However, the coefficient of this linear relationship has these black body radiations, which is strong function of temperature. So in order to get soot volume fraction from this equation, you first need to determine the temperature. This is where the spectral information text comes into play. If you measure emission in a spectrally resolved way, which means you have the relation between this G lambda as a function of lambda, then you can plot then you can make a plot using 1 over lambda as the x-axis and then this log part as the y-axis, and then you will end up with a straight line, and the slope of this line gives you information of temperature. However, there is strong assumptions here, so it has to assume this refractive index of soot, which is m lambda here, is independent on lambda. Otherwise, you will not have a straight line. But this, in reality, this is generally not true, at least in the visible spectrum. So soot particles can have a refractive index that is highly dependent on wavelengths. So this is a big problem. So actually, this plot shows the soot dispersion exponent, which is defined here. You can see this soot measured and the different places inside the same flame can have drastically different dispersion exponent. So actually, but if you only do this spectral soot emission experiment, you will have no information of such dispersion exponent, which makes using this equation to calculate temperature, to derive temperature, very, very challenging. And but I have to mention that this information is given in the visible spectrum or near infrared spectrum. Actually, in this regard, we recently found if you use this mid-infrared spectrum regime, the refractory index is almost independent on wavelengths. So here is our recent work that shows the variation of this refractory index as a function of wavelengths. So actually, we confirm that this in the visible spectrum below 1,000 nanometer, there is a big dependence of this EM as a function of lambda. But if you go beyond 1,000 nanometers, you will see the dependence on wavelengths are drastically reduced. And so that makes us think that if you do this SSE measurement using wavelengths above 1,000 nanometer, then you don't have to worry about this EM as a function of EM as a function of lambda. You just assume it's constant. And actually, we did this, and we used this mid-infrared region to do this measurement. And this is a temperature measurement we did with counterflow diffusion flames. And you can see that the agreement between experiments and the numerical simulation is quite good. And of course, there's only soot in this region, so that's the only region where we can measure temperature with this SSE technique. And once you get the temperature right, then from this equation you can get the soot volume fraction. This is very straightforward. So actually, it has been done by by researchers and Yale. So this is actually what is measured, temperature measured in a soot volume fraction measured in counterflow flames with this method. Okay. The next widely used method for soot volume fraction measurement is night extinction. The principle is also very simple and is based on the fractional absorption of light by soot particles through the Beer-Lamb law. So, but for implementation in counterflow flames, There are two variants. The first one is called this pointwise extinction, where you measure one point of the Soot field every time. Usually the light source you use will be a collimated laser beam. But here is, I just want to mention one thing. You have to be very careful about the beam size, because I mentioned before the counterflow flames has very narrow Soot regions. And if you want to resolve with good spatial resolution, your beam size has to be very small. And our experience is that it's better to restrict the beam to be around 100 micrometers. And if you have a big beam diameter, of course, you will see this profile gets significantly distorted. Another variant is this 2D night extinction method. The principle is actually the same, but now instead of using a single rail beam, you use a large diameter cylindrical shape of beam that covers the entire Soot region, and use a 2D detector, which is usually a camera, as the detectors. So now you can have extinction information of the complete Soot field with only one measurement. However, there is also some complications here. So we know that counterflow flames have a large temperature gradient, and thus they will have also the large density gradient. So once the beam passes through the flame, it can be deflected by this effect. So it now can become quite difficult to know whether the night extinction is caused by Soot absorption or by beam steering. So actually, if you ignore this beam steering effect, you will end up with results that are completely off. So actually, our conclusion is it's not quite possible to use this collimated optical layout to measure Soot volume fraction in counterflow diffusion flames. So another alternative to use a technique called this diffuse back illumination. Here, instead of using a collimated beam, we use a diffuse Lambertian planar light source, and we use convex lens to image the light source and the center of the beam, center of the flame. And after transmitting through the flame, the diverging beam will be re-imaged to the 2D detector, which is usually a camera. This type of configuration significantly reduces the effects of beam steering. I will not elaborate, but if you are interested in why, you can maybe check this paper by Thompson, and that is published in Applied Optics. And in a recent work, we performed the first DBI method study in counterflow flames, and we achieved excellent results that can be confirmed by our LRI measurements, which I will discuss later. So you can see this DBI method as compared to LRI is almost a complete overlap, so confirming the validity of both methods. However, there is also complications for this method. In doing this light extinction method, DBI is also based on light extinction, by the way. So in doing this light extinction method, we need to assume the flame to be axis symmetric, because we need to perform the Abel inversion to convert the measured line of sight integrate extinction to local values. So ideally, counterflow flames can be is axis symmetric, but the problem is if you even have a very slight mismatch between these two ladles, misalignment between these two ladles, you can have the flame that is slightly tilted. And once you have this tilted flame, even though the level of tilting can be very small. For example, there is some numerical simulation we did. Even you have 0.5 degrees of tilting, you will have the measurement results significantly distorted. And this is a big problem, actually. So this is a numerical simulation we performed, and this is the actual experimental observation. You can see that this kind of strange features were all observed in actual experiments. So actually, this is a big problem, because in reality, when you do the measurement, you don't know if your flame is tilted. You cannot see that through naked eyes or even through some magnification cameras. It's difficult to see. You just don't have the reference. So the problem is if you measure something like this, you don't know if your flame is not symmetric or just the Soot field is like this. So there is no way to tell. Actually, this problem, actually, we provide in a recent work a 3-step data post-processing procedure to correct this. I will not elaborate also on the details because it's quite involved. But if you are interested, you can check our recent publication in Optics Express. Okay. A third method for Soot volume fraction is laser-induced incandescence, so which refers to the radiation of Soot particles after being heated up by a high energy laser beams. And if you do energy balance, you will notice that the LRI signal is actually proportional to Soot volume fraction. And that's why it is a promising method for Soot volume fraction measurements. So this is a typical setup for LRI measurement in counterflow flames. The beam is shaped as a sheet to pass the center of the flame. A detection is usually performed normal to the night beam. An advantage of LRI is that it's a local measurement, so there is no need to do the tomographic inversion. So this is a special distribution of Soot volume fraction for these counterflow flames we measured with both LRI and dBi, and you can see almost a complete overlap. Again, confirming both methods. So another point that deserves mentioning is that the laser pulse in LRI measurements is typically very short. So it can be either picosecond or nanosecond. So once the laser is off, the Soot particles will start to cool down so that the emission intensity will decrease. Here, the particles of different size will cool at different rates. So now if you measure the LRI signal in a time-resolved manner, we can get some information to particle sizes. This is actually has been done by a number of research groups, but it has to be mentioned that it's only this LRI, time-resolved LRI is only sensitive to primary particle size, but instead of aggregate sizes. Next, we will move on to temperature measurement. A common method to measure temperature is, of course, thermocouple. So here is the image that where you can see we insert a thermocouple inside the counterflow flames. Maybe this figure is a little bit overexposed, and if you reduce the exposure time, we can see that here the thermocouple wire inside the flame. Okay, since the counterflow flame is temperature is usually quite higher, so the only possible thermocouple type that you can use to measure flame is either type R, S, or B with a maximum temperature of around 2000 K. In counterflow flame, you have to be very careful about several things. First is regarding intrusiveness and spatial resolution, because the counterflow flame, as I mentioned many times, has very steep temperature gradient along the center line. So you have to use thermocouples with very small junctions to minimize intrusion and to achieve the desired spatial resolution. So typically, the junction size will be 10 to 50 micrometers. Even this small, some disturbance of the flame can still occur, which needs to be corrected. A good method is to monitor to see if the position of this blue CH chemiluminescent layer is changed with and without the thermocouple. Another thing is you have to worry about is about the accurate positioning. You have to know the exact position of the thermocouple, because otherwise you will the measured temperature will be completely distorted because very high temperature gradient. So two things can be done. The first thing, you can use a spring to provide tension here to avoid the sagging of the thermocouple inside the flame. It's because this spring can provide tension here. Second thing, you can use a very high magnification images to record the actual junction positions and then do the corrections afterwards. This is some things you have to worry about. There's other things you have to that has to be taken care of when measuring temperature with thermocouple in sooting flames. The first is about the correction for soot deposition. If you insert the thermocouple junction into a sooting region, soot will be deposited on the junction through small phoresis effects. The result is actually a reduction of junction temperature with time. And this effect has to be corrected and can be corrected by doing extrapolation to time 0 when you insert the thermocouple. So that's why in this setup, you can see we use a laser as just as a trigger signal to know where we have time 0. Another thing is about this standard radiation corrections, which is actually very important. And basically, you just write this energy balance equation, and you want to derive the gas temperature with this measure the junction temperature. And this equation involves a lot of things. So you involve the diameter of the junction, the Lucille number, which is actually depending on the gas composition. And this kind of correction turns out to be very important, especially in this peak temperature region. So you can have the correction, and the level correction can be as high as 200, even 300 degrees K in some cases. So this is very, very important to do. A third thing is about these kinetic effects, because all these R, S, or B types of thermocouples are made of platinum, which can be quite catalytic. So in many cases, you probably need to do some ceramic coatings to avoid this catalytic effect. But the good news is if you do all the corrections and consider all the subtleties I just mentioned, it's possible to measure temperature in counterflow flames with thermocouple. And this is has been done. This is an example that was done by the Yale group. You can see this measure the temperature agrees quite well with the numerical simulations. It's with very high spatial resolution. Just keep in mind it's only 1 millimeter. Here you have a temperature drop about 7 degrees. So this is actually very good. But to be honest, I'm not a big fan of this method, although I have performed this by myself. But this method, you have to consider too many things, too many corrections. What I prefer is this non-intrusive temperature measurement method, which is based on laser absorption spectroscopy. So basically, certain species in the flame is based on the fact that the certain species in the flame can absorb light and a specific wavelength. And temperature and the mole fraction of the data can be obtained from this absorption spectra. So here is a typical setup used for laser absorption spectroscopy for temperature measurement in our lab. And one important decision you have to make is which species you want to target. There are several criteria that you need to consider. For example, the peak temperature, the line strength, and the interference in the free space, and etc. So finally, we choose to target the CO2 species, and we select the R branch of the bandhead of the new Swiss fundamental of CO2, which is nether beam is around 4.2 micrometers. It's in the mid-infrared region. So actually, if you look at this simulated spectra, you can see this choice is quite good because it has very line strength and high temperatures, but very low line strength and ambient temperatures. So if you look, the reason why we need this is if you look at this plot, the beam has to transmit in free space for quite some distance before it reaches the flame. So you don't want absorption in this region, and you only want absorption in the high temperature region. And that's why we choose this type of absorption features. And actually, we use this method to measure flame temperature for 4 different counterflow flames. 2 of them are sooting flames, and 2 of them are non-sooting. And this temperature we measured for the first 2 flames is a typical Soot formation flames, and this is you can see a very good agreement between the measured temperature and the numerical simulations. And in the same time, we can get the CO2 concentrations, which also compared very well with the simulation. And this is a very high temperature. So you can see the peak temperature here is around 2200 K. So it's I think it's quite impossible to measure this with thermocouples. And this is the only way to measure this high temperature is through this non-intrusive method. Actually, this method is a workhorse now in our lab to measure temperature field in counterflow flames, because you don't have to worry about the intrusiveness and all the corrections I mentioned for the thermocouples. Okay. Okay. If you look at this setup, you can see that this is very similar to the one that we use for Soot volume fraction measurement. So that makes us think maybe we can use the same setup to measure Soot volume fraction temperature simultaneously. This actually we were actually successful in doing this. I will not elaborate on the details, but one thing I might need to emphasize is that since we are now using this mid-infrared, which is 4.2 micrometer laser source, and if you look at these equations, you will notice that for the same Soot volume fractions, if you use longer wavelengths, your measured extinction ratio will be inversely proportional to lambda. So that means if you use longer wavelengths, your signal to noise ratio can be significantly compromised. So to solve this problem, we actually use intensity modulation techniques and to enhance the signal noise ratio. And with these techniques, we're actually successful in measuring this temperature, Soot volume fraction, and the CO2 mole fractions in one laser scan. So this is some plot, some data we measured for the 2D distributions for the flames, and these things are measured simultaneously, temperature, CO2, and the Soot volume fractions. And if you're interested, you can go check our recent publication. This work was published in Applied Physics B in 2022. Okay. So there's another non-intrusive temperature measurement, which is spontaneous Raman scattering. So this method can measure both temperature and the measure species. However, the signal is very weak, so it can be easily buried in other signals, such as pH, lift signal, or LI signal in sooting flames. So Raman scattering previously was mostly restricted in non-sooting clean flames. Very recently, the research from the Aachen University proposed a short-gated detection technique that they used to perform this spontaneous Raman scattering in counterflow sooting flames. That was successful, but they also mentioned that the method is only applicable to very low sooting flames. So their test case have only a peak-through-volume fraction of 0.1 ppm, but in reality, if you increase, they said that if you increase the through-volume fraction to, for example, 0.15 ppm, the method will not work. Still, because of this strong interference from these broadband emissions. Okay. About next, we'll talk about these species measurements. So we have both the non-intrusive optical methods and intrusive probe-based methods for species measurements. So the non-intrusive method generally including as I mentioned, laser absorption, lift, or this Raman scattering, but they are mostly restricted to small species because these large molecules typically have very complex molecular spectra that is not suitable for quantitative measurements. So, however, for soot studies, you usually want to get information on these not complex molecules. For example, soot precursors, which are mostly PAHs. So in that case, you have to rely on this sample probe-based methods such as GC, GCMS, or this molecular beam mass spectrometry. So this is a typical setup we use in our lab for GC measurements. And you can see here the probe is inserted into the flames. And also, if you look at this GC setup, because in many times we want to measure both the major species and the minor species and also pHs, we typically use a variety of GC columns to separate different types of species and use different detectors for different species, for example, TCD, FID, and the mass spectrometry. Here is a typical metadata in sooting counterflow flames. As you can see, we can measure the hydrogen, acetylene, benzene, and naphthalene, so which are two ring aromatics. One thing that I would like to mention is about the calibration. So for small species, the calibration is relatively easy because you can just purchase standard calibration gas cylinders. But for large species, for example, PAHs, you have to you will need the liquid samples, and then it is very important to design a reliable system that you can accurately feed the sample into the GC system. This is actually, from our experience, not trivial. But most recently, pH up to 6 rings has been detected in the counterflow flames, which is quite remarkable. This is a work again done by the Yale group. Of course, some enrichment techniques need to be used, and I will not elaborate, but it's possible to measure 6 ring aromatics, which is quite remarkable. And there are some subtleties I have to mention for this GC probe sampling. The first thing is we need to consider is, again, intrusiveness. We should use sample probes that are as small as possible. And the typical inner diameter of the probe is around 70 to 100 micrometers, which needs to be even smaller if you are measuring for high pressure or high strain rate flames. Even with such a small probe, you can probably still have non-negligible probe effects. For example, your measured profile can be shifted in space because the probe effects on the flow field. So one way to correct this is in our lab, what we did is to compare these results with the non-intrusive methods. For example, the laser absorption spectroscopy I just mentioned. So here you can see two profiles. One is measured by GC, the other one is measured by optical methods, and you can see clearly a shift, which you can correct afterwards using by comparison the two data sets. In sooting flames, you have to also worry about this probe clogging, and once that happens, you have to remove the probe and send it to an oxidizing environment, burn it off. So actually, this type of experiment is quite time-consuming. Another one is in high temperature region, you may also have probe bending because of this force can be softened by the high temperature in high temperature environment, and you have to also correct for that using probably high image still images to track the exact location of this probe. And if you are measuring large species such as pHs, you have to also worry about sample condensations. You have to, it's recommended to use very short sample tube lengths, and you heat up the sample tube and reduce sample tube pressure. So there is a lot of subtleties. The principle is easy, but to measure correctly in counterflow flames is many times quite challenging. So I think for the sake of time, I probably have to skip this slide. But what I just want to mention here is GC method, you cannot preserve the radicals. So if you want to measure some important radicals, for example, proprietary radicals, you have to rely on molecular beam sampling. So actually this was done by Sandia group, by Professor Dr. Neil Hansen and Sandia's group. You can measure proprietary radicals, which is quite remarkable. Next thing is about the fluid field measurements. There's not so much to say because it's quite conventional. This is just a setup we use in our lab for PRV measurements. So there is some rule of thumbs, but I will not elaborate. But you have to just worry about the trace density and the time interval between the pulses. This is the actual measurement of the axial velocity. You can see this agrees quite well with previous measurements using LDV, but this PRV is much simpler, and you can just take the measurement with two nether pulses. Otherwise, if you use LDV, you have to scan the field because it was a point measurement. So that's so much for the measurement part. Next, I will talk a little bit on this modeling aspects. First, I want to mention that in many cases, we will model the counterflow flames called one-dimensional. When modeling as quite one-dimensional, we need some boundary conditions, and the velocity boundary conditions we need to feed into the model is generally the axial velocity and the radial gradient of radial velocity and the nodal exit. In many cases, we will assume a plug flow and simply use the flow rate divided by nodal exit area to compute the average velocity to feed as boundary condition, and assume there is no radial component. But this is not the case in reality, especially when you use counterflow burners with contoured nodal without flow straighteners. Here is the actual measured velocity profile and the nodal exit across the nodal radius. You can see the actual velocity differs notably from the average value. So if we provide this average value in the model, you will end up with significant different predicted profile. So here you can see this solid curve is simulation with this actual boundary conditions, and this dashed curve is with this average velocity as boundary conditions. There's a huge difference, and if you have this, you can. It will be difficult to tell if your model is failing or just the chemistry is not working. So it's important to have the accurate boundary condition. But the question now is, how do I obtain correct boundary condition? If I do not have the PRV measurement in my lab, how do I know the boundary conditions? So actually, we noticed that this boundary conditions can be obtained by doing very simple 2D simulations that include the burner geometry. And when I say simple simulation, is just you can do this with just one-step chemistry, and the results will be the results for the boundary condition will be accurate enough for you to use in subsequent 1D model with complex chemistry. Okay, this is one part. Another thing is about the modeling of counterflow flames. Is about the curtain flow. And we know that the sooting counterflows is typically fuel rich, so there is a possibility that some unburned fuel that mix with the ambient air to form this type of secondary diffuse flame. This is actually quite undesirable, and we usually use a curtain flow to quench this flame. But in many studies, this curtain flow is not considered, it's not taken into consideration. We do actually observe this curtain flow rate can affect the central counterflow flame, and it needs to be considered when modeling. And our results or our finding is that this curtain flow affects the flame only through modifying the boundary conditions. So if you again get the boundary conditions correct, then there will be no problem. So the current flow will not affect any structure other than that. So this is one conclusion we have made, and if you're interested, also recently published this work in physics of fluids in 2023. Okay. So finally, I would like to describe some of our recent work on measurements in oscillating flames. The motivation of doing oscillating flames really has to do with these two temporal terms in the Laminar equations. For the static Laminar models, these two terms is generally neglected. So the Laminar equation can be solved separately without considering the flow field. So the results can be tabulated, which is a very efficient model to use. I think it's just anyone who is doing turbulent combustion modeling will know what I'm mentioning here. Actually, we use this laminar flame model for simulate counterflow flames in 2 dimensions. And there is some slight difference between conventional flammid and flammid for counterflow flames, because now you have 3 streams, you have fuel oxidizer and curtain flow. And so you need 2 mixer fractions. So this is actually firstly proposed by this Professor Bissetti in 2020, but we follow this method. We create this flammid model and we use it for simulation of these 2-dimensional counterflow flames, and we see a reduction of computational time by 600 times. So which means this model is actually very useful for simulating these flames. But the problem is, if you want to target soot or NOx, which have soot or NOx, which have very slow chemistry, then this assumption will not work. So you have to consider this oscillating effects. That's the reason why we are doing this oscillating flames. We want to know the oscillating effects on soot formation. So this is the primary reason of our recent work on oscillating flames. So a very good way to investigate this oscillating effects is through this counterflow flames with oscillating strain rate. So this is a schematic of the oscillating burner that we use in our lab. So we actually use a loudspeaker installed on both sides to generate the velocity oscillations and the nodal outlet. And the driving voltage of the loudspeaker was provided with a controlled frequency and amplitude, and to generate this type of oscillation in the axial velocity profile. So this is if we can adjust the frequency and the amplitude to see the response of soot volume fraction soot measurement. So once we have this oscillating flame set up, we perform time-resolved soot measurements with either phase-locked LRI or the dBm, as I mentioned earlier. So here is our measurement for typical oscillating flames, where the black symbols measure the peak soot volume fraction as a function of time. The blue is measure the global strain rate, which is from the PRV measurement. Also included is the soot volume fraction if measured in static flames. So actually, the difference between the black curve and the gray curve is what we call the unsteady effects. So you can see this unsteady effects is characterized by the notable phase delay and the amplitude reductions. And this is only for one the oscillation frequency. If you increase the oscillation frequency, you will see the unsteady effects become stronger and stronger, which is much as expected. And what is interesting is that we actually compare the flame of 2 different fuels, and we see a dependence of these unsteady effects also on the type of fuels. So compared to the ethylene flames, the propane flames has a higher oscillation amplitude. This is a very interesting observation. But what's even more interesting is that if you keep the strain rate effects of soot volume fraction matched in static flames, and all static effects becomes quite identical. This is I think a very novel observation, and it can be of some usefulness for the developing unsteady model for soot formation in turbulent diffusion flames. I don't have time to elaborate quite much on this. Apology for that. But if you are interested, there is 2 recent publications on this specific point. You may wish to look and take a look. Okay. So lastly, as a general remark, I would say that we know the soot formation is quite complex, and I believe laboratory flames with highly controlled boundary conditions are important research platforms. And high-fidelity measurements of multi-parameters and modeling with real boundary conditions are important for assessment and development of predictive models. And also, if there is any new mechanisms that describe Soot formation, that should be converted to models that can be experimentally validated. Okay, so that's all for my presentation today. So I have several people to acknowledge. First, I would like to thank Professor Suku Chiang, who is my PhD advisor. And also, I would like to acknowledge Professor Alejandro Gomez at Yale, who shared a lot of information on how to measure accurately sooting counterflow flames. And lastly, I will also acknowledge the members of our lab and the National Science Foundation of China for funding support. Okay, thank you all for your attention.